Good afternoon. I'm Mr. Ish. You're joining me for this part 2 to the hyperbolic. Part 1 was where we were looking at the hyperbolic sine. Part 2 here we're looking at the hyperbolic cosine derivative, derivation, or proof, as you might want to call it. The derivative of hyperbolic cosine hx is equal to sine hx. Very well, look at the video we've shown you before this. It has many of the same things which will show up over here. How is this the case? E to the x plus e to the minus x over 2. This is the definition of the hyperbolic cosine. When you do the derivative of this using the exponential derivative template, you know that's a e to the ax. When you use these exact same principles right over here into this form, you'll get e to the x minus e to the minus x over 2, which is the hyperbolic sine. So you know that. Also remember this, as I was talking in the previous video, hyperbolic sine of 0 is equal to 0. Hyperbolic cosine of 0 is equal to 1. And for this one, the specific identity you need to know for the hyperbolic is the hyperbolic cosine sum formula. This will be mirroring the trigonometric sum formula but slightly different, and this is what it opens up into: cosine hx, cosine hy. The difference here is you retain a positive. In the trigonometric version of this you have a minus here, and this is sine hx, sine hy, and everything here you need to know for the actual limit derivation, which is the formalized approach to this proof. The formalized limit approach, which is a better approach, more lengthy but better, follows this format which you should now be familiar with. You've seen this quite a few times, that it shouldn't be too hard. How do we start? Everything will go right here into this with regards to what you're seeing over there. Limit as h approaches 0. We'll have cosine hx plus h minus your f of x, which is cosine hx all over h. You have to open this up using the identity I've shown you, and we will do that. Limit as h approaches 0. You have cosine hx, cosine h of h, we should be bringing in these parentheses so we don't get lost in the letters, plus sine h of h, and then sine h of x minus cosine hx, right? All over h. Again, you will isolate and identify the common terms, which are this, and this right here is separate. I'm going to, in this step, do the exact same thing I did with the other one. You see, you have in this one cosine hx, here you have a cosine hx, you can isolate the cosine hx, which I will do. And it goes in this first term, cosine h times, and it goes in the second term, 1 time, minus 1 time, all over h. We have a plus over here, limit as h approaches 0, we have this. I'm writing the x component for sine h of x, and then sine h of h all over h. We have these things in a product relationship, this with that and that with that, which I'm going to separate now using their individual limits, using the product property of limits. Limit as h approaches 0, we have cosine hx times limit as h approaches 0, we have cosine h of angle h minus 1 over h. You see, you get an indeterminate limit form come over here, as you will right over here. Limit as h approaches 0, you have sine hx times limit as h approaches 0, you have sine h of angle h over h. Come down right here. Cosine hx, limit as h approaches 0, retains itself and it stays as cosine hx. Look right here. This is a 0 which will come right here in places of h. Cosine h of 0 is a 1. 1 minus 1 is a 0. 0 divided by 0. You have an indeterminate limit form for which you can use the L'Hopital's rule procedure, derivative of the numerator and the denominator with respect to h. Right here, exactly the same will come into play. You put 0 here in places of h. Sine h of 0 is a 0. 0 divided by 0, you have an indeterminate limit form. We will look at this part first. When you do the derivative of the numerator, you'll get sine h of angle h over 1, and you can put a 0. When you put 0 now in here to test if the indeterminate limit form exists, you get a 0 over 1. Remember, 0 over 1 is not an indeterminate limit form. 0 over 0 is. When you get 0 over 1, it's equal to a 0. All of this right here boiled down into a 0, which multiplies with cosine hx, and you have this plus right here. Sine hx with regards to its limit retains a sine hx. When you come over here, you do the derivative of the numerator, you get a cosine h of angle h. Derivative of the denominator with respect to h is a 1, you can put a 0. When you put 0 in place of cosine h of this h right here, you get a 1. 1 divided by 1 is a 1. All of this breaks down into a 1. this 1 multiplies with this sine hx, and it gives you exactly what you wanted. The derivative of hyperbolic cosine is a hyperbolic sine, and derivative of hyperbolic cosine hx is a hyperbolic sine hx, and you are done. And the derivative proof has been completed, just very well like how you saw with the previous video on the hyperbolic sine. Following a very similar format, both of these different hyperbolics, as were the trigonometric sine and cosine functions. So keep all of this in your mind. I appreciate everyone watching this and my videos. Have a great day. Thank you.